So what happens now as x goes to negative infinity or positive infinity? That's something we got to take a look at. That's different because how do you plug in infinity? Eh? So yeah, this looks like 2 times negative infinity cubed over 3 times negative infinity squared. Yuck. Okay, so here's what we actually know a way to do this already, and we'll bring that up in a bit. Okay, first off, here's what we got to do. So what's the highest power of x in the denominator? So in the denominator, you got x squared. And again, the denominator is always usually the problem. So that's usually where we focus our attention. So since it's x squared in the denominator, let's get rid of x squared in the denominator, sort of, quote, get rid of it. So what we're going to do, we're going to take and divide by x squared, or multiply by 1 over x squared. And of course, what we do to the numerator, we have to do to the denominator. Okay, so when we do that, you get the limit as x approaches negative infinity. 2x cubed times 1 over x squared is 2x over. So 3x squared divided by x squared minus 2 divided by x squared. And it doesn't seem doesn't seem nice at all right now off the top of your head looking at that, or right now going, huh? What's worse? Yeah, you're right. I understand that. But we've got this one thing here, this one limit that's going to help us out. The limit as x approaches to infinity, whether it's positive or negative, doesn't matter, of 1 over x. And actually, it doesn't matter if it's x or x to any power. This limit is always going to be 0. Again, think about it. We've got 1 divided by a really big number, the reciprocal of a really big number. So if you think like 10 to the 100th power, so 10 to the 100, reciprocal is 10 to the negative 100th power. That's an itty bitty number. So that's what happens. So now, what do we do with this? Well, when we're in this case, with this setup here, so go ahead and pretend, let's see if negative infinity, treat it like a number. So 2 times negative infinity, it's going to be a negative infinity. Well, the limit as x goes to negative infinity of 3, well, the limit of a constant is just that constant. Minus, so the limit as x goes to negative infinity of 2 over x squared. Doesn't matter if we multiply by 2 or x squared. This, again, 2 over a number getting really bigger, ends up being 0. So if negative infinity divided by 3, that's negative infinity. Now, that's fine and dandy for an answer. I know negative infinity is not a real number here or within the limit either. So we're looking at behavior, and that's the key. It's behavior. Okay, so let's scoot down to something like let's take 64, for example. And highest power of x in the denominator, it's x squared. So we're going to multiply by 1 over x squared, or divide by x squared. And again, multiplying the whole thing. Again, we can do that because x goes to infinity. So x divided by x squared, 3 divided by x squared, over 2x squared divided by x squared, 2x divided by x squared, well, there's an extra factor, x in the denominator, and then 1 divided by x squared. Again, doesn't look very nice now, but again, if we go back to this special limit right here, that makes things a whole lot nicer. So as x goes to infinity, 1 over x goes to 0. 3 over x squared, as x goes to infinity, goes to 0 also. the limit as x goes to infinity of 2, hey, constant is, the limit of a constant is always that constant. So the limit as x goes to infinity of 2 over x. Limit as x goes to infinity of 1 over x squared. Again, as x gets really large, 1 over x gets really small really quickly. That's it. So 0 over 2 is 0. So there's your limit. Again, behavior. We've seen this before. What side of the graph would x go to infinity be on? The right or the left side? Exactly. This was our right-hand behavior. So when x goes to negative infinity, like over here, that's our x going to negative infinity would be our left-hand behavior. Remember the disco math? Also, we've seen this before with the different degrees, same degrees or different degrees. This is a horizontal asymptote. So when we look at, does this function, this rational function, have a horizontal asymptote? We just take the limit as x goes to infinity. If it turns out to be a real number like this, that's a horizontal asymptote. If it doesn't become a real number like up here, that's not a real number. You're right. We don't have a horizontal asymptote. We have an oblique or a slant asymptote, depending upon the degrees. So that's how these limits tie into what we had before. Okay? So if you remember those shortcuts from back then, the rational expressions, go ahead and use them. Again, that's as long as x goes to infinity. Let's look at 57. I just want to look at it a little differently because it is a one-sided limit. So if we try direct substitution, so negative 5 plus 4 over negative 5 squared plus 9 times negative 5 plus 20, we get negative 1 over 0. Well, if it was just the limit as x goes to negative 5 without the positive side, we'd have the limit doesn't exist. However, one-sided limits actually are behavior. So we can do a little bit more. I'm going to go ahead and factor, see if I can factor either numerator or denominator. Now, one thing, notice it's not 0 over 0. It's not our indeterminate form. So we may not be able to cancel anything out. Actually, it turns out, though, in this case, we can. Okay? So if we go ahead and cancel those out, we can. So an equivalent function, an equivalent limit, except that x equal 4, but we don't care about 4 because we get, or negative 4 because we got negative 5 here, this function. So now, how about this? What happens? Now we know if we plug in 0, if we plug in negative 5, we get 0 again. But what if we plug in a number super duper close, but just to the right, just greater than negative 5? So we get 1 over, now a number x plus 5, when we're at negative 5, exactly at negative 5, we get 0. But if we're real close, we're about 0. But for the right side of negative 5, is x plus 5 positive or negative? Yes, it's a little bit of positive, little itty bitty positive, like negative 4.99999999994. This number is almost 0, but positive. So 1 divided by a really small number, or the reciprocal of a really small number, actually is a really big number. And because it's positive, positive infinity. Again, we just got this one here, just wanted to look at what that kind of thing. By the way, what kind of behavior does that do? If you think back to the graph, the rational function graph here, at x equal 5, negative 5, since it's not removable, we'd have a vertical asymptote, and the right side of that would go, so if this is here at -5, our right side would be like that up to positive infinity from the right side of that vertical asymptote. Again, not really a big thing we're pushing today, but just wanted to show you that. So work on the others. If you know remember the shortcut, great. If you don't, go ahead and do that. Be careful with this. What is the essential power here? I'll let you work with that, and we'll fiddle the rest of this as we go through, especially on Thursday. Hammer out any other questions. All righty.